Alice, Bob, and Eve explain quantum error correction.
I have finally been wrapping up my Christmas tree ornaments. A lot of work, since each ornament needed its multiple layers of tissue paper. If one layer gets torn, the ornament is still protected.
That's actually a perfect analogy for quantum error correction. It's one of the most important concepts in quantum computing.
Quantum error correction is fascinating. It's how we protect quantum information from noise and decoherence.
How do my wrapped ornaments relate to quantum computers?
Quantum bits, or qubits, are incredibly fragile, like your ornaments. They can be disturbed by tiny amounts of heat, electromagnetic radiation, or even slight vibrations.
But unlike classical bits that are either 0 or 1, qubits can exist in superpositions of both states simultaneously. That makes protecting them much harder.
So how do you protect something so delicate?
We use redundancy, but in a quantum way. Instead of storing information in a single qubit, we spread it across multiple qubits in a special entangled state called a logical qubit.
It's like how you're not putting all your trust in a single layer of tissue paper. The quantum information is encoded across multiple physical qubits, so that damage to a few of them doesn't destroy the overall information.
But how do you check for errors without disturbing the quantum state? I thought measurement collapses superpositions.
That's the clever part. We don't measure the quantum information directly. Instead, we measure properties called error syndromes that tell us if and where an error occurred without revealing the actual quantum state.
It's like checking if your box with ornaments has been tilted without opening it to look at the ornaments. We can detect if something's wrong without disturbing the fragile contents.
What kinds of errors can happen to qubits?
Two main types: bit flip errors, where a ket 0 becomes ket 1, or vice versa, and phase flip errors, which affect the quantum phase relationship. We need codes that can detect and correct both.
The simplest code, the 3-qubit bit flip code, uses 3 physical qubits to encode 1 logical qubit. If one flips, the majority vote tells us which one is wrong.
But that sounds like it would only protect against certain kinds of errors.
You're absolutely right. More sophisticated codes, like the Steen code or the surface code, can handle both types of errors and scale to protect many logical qubits.
The ultimate goal is to reach fault tolerance, where we can perform reliable quantum computations even when components are imperfect.
That sounds like it requires a lot of extra qubits.
It does. Current estimates suggest we might need 1,000 or more physical qubits to create one fully error-protected logical qubit. That's why building large-scale quantum computers is so challenging.
So my carefully wrapped ornaments are like error-corrected qubits. The valuable information is protected by layers of redundancy, and there are ways to check for problems without unwrapping everything.
Yes, and just as your careful packing means these ornaments will survive to next Christmas, quantum error correction is what will allow quantum computers to perform reliable calculations despite their inherently fragile nature.